Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at an example problem for drying. So let's read together the problem statement. It says that a filter cake that's 24 inches by 24 inches, so, these are the dimensions this way, and then it's 2 inches thick. And it's supported on a screen so that it can be dried from both sides. It has a wet bulb temperature of 80 degrees Fahrenheit, and it has a dry bulb temperature of 160 degrees Fahrenheit. The airflow is going to be parallel to the faces of the cake, and it's going to be at a velocity of 8 feet per second. The dry density of the cake is given is 120 pounds per cubic foot when dry. And we can ignore the equilibrium moisture content. Under the condition of drying, the critical moisture content is 9% on a dry basis. And what we want to find is the drying rate during the constant rate period and how long it will take to dry the material from an initial moisture content of 20% to a final of 10%. And we'll assume an effective diameter of 6 inches. So in this case, first we're going to need some data. And so from data tables, we find values of the heat of vaporization, the viscosity, the Prandtl number, and the conductivity for this. And so we need to calculate the density as one of the pieces that we will need. And I'm going to assume that this acts as an ideal gas. So our pressure is 14.7 psi, molecular weight 29, I don't know where I got a 29 pounds mass per pound mole. And then we'll divide this by R 0.732 cubic feet psi per pound mole degree R and 620 degrees Rankine. And so the density is 0.0641 pounds mass per cubic foot. Now we need the gas flow flux, okay? So we're going to start with our velocity, which is 8 feet per second. And 3,600 seconds in an hour gets me on a per hour basis. And then multiply this by my density. And I get 1,845 pounds mass per square foot per hour. Yes, per hour. Okay, and then we can use this for the Reynolds number, and for these units, dg over the viscosity will get me Reynolds number. So my effective diameter is 6 inches or half a foot, to save on writing that. G is 1845 pounds per square foot per hour. Mu is 0.0205 centipoise, and I can change that to pounds per foot per hour using this conversion factor. And so we end up with a Reynolds number that's 1.86 times 10 to the fourth. Okay, so we've already found from data the Prandtl number is 0.69. The Reynolds number we just calculated to be 1.86 times 10 to the fourth, and now we want to use this to find the rate. So the rate of vaporization, or drying, is going to be related to the heat transfer coefficient H, and we're going to find that using a Nusselt number. And if you browse through the equations that we have available to us, you'll find 0.037, Reynolds number to the 0.8, Prandtl number to the 0.33, is the appropriate equation for this situation, and that gives us a value of 85.2. I can now use this to find H as the Nusselt number times the thermal conductivity over that effective diameter. So the Nusselt number is 85.2, K is 0.0171 BTUs per hour foot degree Fahrenheit, and the effective diameter again is 0.5 feet, leaving me with a value for H of 2.9 BTU per hour foot square degree Fahrenheit. And next I'll use this to calculate the rate, which is basically just that my amount of heat transfer, or H delta T, is equal to the drying rate times the heat of vaporization. So I can divide H delta T by the heat of vaporization. So the H I just found was 2.9 BTUs per hour foot square degree Fahrenheit. My delta T given is 160 minus 80. And the heat of vaporization from data was 1049 BTUs per pound mass, and this leaves me with R is 0.221 pounds mass per hour per square foot. All right, so we just found R is 0.221 pounds per hour per square foot. And we know that the geometry, that this is a plate that's 24 inch by 24 inch, or since we're working in feet, 2 feet by 2 feet, and then it's 2 inches thick. So we also know that the drying is going to be from both sides, so the area is going to be the area of one side, so 2 foot by 2 foot, and then multiply that by 2 because it's both sides. And so therefore we're going to get 8 square feet is our area. And the rate of drying then is just going to be just the product of our R times our area. So R was like a flux, it's per square foot, so we're multiplying by our 8 square foot for both sides of this thing. And so our mass of water removal rate is 1.77 pounds of water per hour. Now we also are going to need to do some calculations on the cake. So first let's figure out the volume of the cake. The volume of the cake is just the 2 foot by 2 foot times 2 inches, so 2/12 of a foot. And so it's 0.667 cubic feet. Now notice that I'm not using the 8 square foot because that was taking the surface area on both sides. This is just the area of a cross section. And now we can use this with the density of the dry cake to find the mass of the dry cake. All right, so the mass of our dry cake is 120 pounds mass per cubic foot, the density of the dry cake, times the volume of that cake, leaving us with 80 pounds mass of the dry cake. Now we want to figure out how much water is needed to be vaporized. And so if I have 80 pounds mass of dry cake and we're going from 20% to 10% on a dry basis, then 80 pounds mass times 0.2 minus 0.1, leaving me with 8 pounds mass of water that needs to be vaporized. And I can use this with my drying rate to estimate the drying time. I'll estimate it as the amount of water to be vaporized, so 8 pounds mass, divided by the rate of water removal, which is 1.77 pounds mass per hour. And this estimates that it will take about 4.5 hours to remove the necessary water. So this concludes this example. Thank you very much for your time.